In this lesson, we are going to discuss some important points about spring block system. We had got the formula T equal to 2 pi root over m by k for a horizontal spring block system. The same formula is applicable for a vertical spring block system. Only thing is that now the mean position will be different, in the sense the spring will not be in its natural length. When you hang this mass, mg is acting down, and to balance this, the spring will extend. So in equilibrium condition, let us say the extension of the spring is L. So there is a force acting in the upward direction, K into L. So K into L will be equal to mg. This L is not length of spring. L is equilibrium extension of the spring when the mass m is hung. So from here we get m by k equal to L by g. And therefore, the time period of a vertical spring block system can also be written as 2 pi root over L by g, where L is not the length of the spring. L is the extension of the spring when mass m is hung. Now, seeing this equation, you may think that the time period of a vertical spring block system depends on g. But actually it does not depend on g. It depends on m and k. If g changes, if g increases, then L will increase, because L is the equilibrium extension. If g decreases, L will decrease. Therefore, time period of a vertical spring block system does not depend on g. Now we can connect springs in series and parallel. Suppose we connect springs in series. Then what will be same for the two springs? We are assuming that the springs are massless. So this is one spring, the other spring is connected to this, and both the springs are massless. So therefore, the force acting on them will be same. Like for a massless string, tension is same at all points. For massless springs, the force acting on this spring and this spring will be same. So therefore, in this case, F is same. Now, this spring, if it gets extended by x1 and this spring by x2, then the net extension is x1 plus x2, and this will get added. So x gets added. So x is equal to x1 plus x2, and F is equal to kx. So x will be F by k. So where k is the equilibrium spring constant, and x1 will be F by k1 and x2 will be F by k2. Therefore 1 by k is 1 by k1 plus 1 by k2. So when springs are connected in series, the force is same and x gets added, and the formula for springs in series is similar to the formula for resistors in parallel. 1 by k is 1 by k1 plus 1 by k2. Now, if we connect the springs in parallel, what will we say? So this is one spring, this is another spring. Now they are connected in parallel, and this mass does not rotate, it just comes straight down. So if it comes down by x, both the springs will get extended by x. So in this case, x is same. So when springs are in parallel, x is same. Now this spring will exert a force upward F1, this spring will exert a force F2 upwards. So therefore, the net force on this mass in the upward direction will be F1 plus F2. So F gets added. So when springs are in parallel, F gets added. And this F is equal to F1 plus F2. So F is Kx. So this net force will be K equivalent into X. F1 is K1 into X. And F2 is K2 into X. So we get K equal to K1 plus K2. The formula for springs in parallel is similar to the formula for resistors in series.